This is the video abstract of the paper titled New Convolutional Neural Network Classification Model for Missing Solder Balls Detection in Encapsulated Semiconductors, which was submitted to the IEEE Latin America Transactions for its evaluation and possible publication on the journal. This document describes the design and implementation of a new CNN-based algorithm for the automatic detection of missing solder balls in encapsulated semiconductors. The proposed algorithm utilizes a customized CNN model architecture that is designed to perform the classification of this specific fabrication defect. The dataset for training and testing was built from 51 images of solder ball grid arrays with at least one case of a missing solder ball. The images were captured by a semi-automatic inspection machine with a controlled light source and fixed camera parameters, which is part of the production process in an internationally renowned semiconductor company. The images of the ball and missing ball classes were segmented using a proposed pre-processing algorithm, which uses thresholding, binarization, filtering, and linear regression to estimate the size and position of the solder ball grid array, where solder balls should be. As a result of this pre-processing, 1330 and 95 images of the ball and missing ball classes were obtained, respectively. Due to the high unbalance of the classes, the images of the missing ball class were oversampled by duplicating the images in the class until the same quantity of images in the ball class was reached. The 80% of this dataset was used for training, and the remaining 20% of images was used for testing of the proposed model. Additionally, data augmentation techniques were used for training, including rotation, horizontal and vertical scaling, horizontal flipping, and pixel filling. The proposed model architecture consists of the following layers. First, 3 blocks of Conv 2D and max pooling 2D layers. The Conv 2D layers have 32, 64, and 128 filters respectively and use the ReLU trigger function. Max pooling 2D layers are used to reduce the spatial dimensionality of the convolutional layer output. Second, a flatten layer to flatten the exit of the last Conv 2D block. Third, 2 dense layers with 128 and 64 neurons, respectively, and ReLU activation functions, regularized with L2 and with weights initialized using the Glorot normal initializer. A dropout layer after each dense layer is used to regularize the model and reduce overfitting. Fourth, a dense layer with neurons equal to the number of classes and softmax activation function for classification, also regularized with L2 and with weights initialized using Glorot normal. Additionally to the proposed model, 2 pre-trained models based on VEEG G16 and MobileNet were modified and fine-tuned on our dataset for comparison. The experiments conducted show that all the models in comparison achieved an accuracy of 93.3% with multiple hyperparameter configurations. However, taking F1 score as the reference metric for this highly unbalanced dataset, the proposed model presented the best performance, reaching up to 90.5% of F1 score for several configurations. Moreover, statistical analysis of the classification metrics for all hyperparameter configurations shows that the proposed model obtains the best overall performance, since it shows a more robust and consistent performance with respect to the other models in comparison. Therefore, the obtained results demonstrate the feasibility of integrating the proposed model in a realistic production environment. Finally, as future work, it is desired to explore the implementation of models that can infer whether there is a missing ball from the picture of the entire component. Improving the dataset by increasing the number of samples of the missing ball class and the real-time implementation of the proposed model in a semiconductor production environment are also considered. Thank you very much for your attention.